So we talk about differentials. This is a cool section. I'm going to show you how it's used for some applications in engineering, some physics. So we'll talk about that in a little bit. However, what I was mentioning to you before I started this was a lot of times people don't even get differentials from Calc 1. A lot of calculus professors, teachers just skip it. So I need to give you, and I know that that's the case for many of you, for most of you. So I'm going to give you an introduction to differentials from Calculus 1, and then we'll make a jump to Calculus 3. It's not much of a jump, but I need you to understand the Calc 1 differential very well, because the proof for differentials in Calc 3 is based on that understanding. And that's what I need you to get. Does that make sense? You're like, no. Well, it will. It will. Just wait for me. So differentials. Here's the basic idea of what differentials even do from a Calc 1 standpoint. So here's differentials from Calc 1. Imagine you have just this curve. And we've got 2 points on this curve. Our famous P and Q. So basically what we always practically have. And here's our x-axis. And we're going to say that at the point P, we call that x. And at the point Q, we're going to call that x plus a little bit. We could do x plus delta x, x plus h is like the traditional notation, like x plus a little bit. And the idea behind all of calculus was, all right, so if we want to find a tangent line at P, what we do is we let delta x go to what? And the 0 pulls this point closer to this point, and we define that derivative as the slope of the tangent line at the point P. We let Q get really, really close to P, and we say that right there, when we let that happen, the limit as delta x approaches 0 of the slope here gives us the slope of the tangent line at the point P. That's what we say. That's what a derivative is. Now, what's a differential? How's that differ from a derivative? Well, let's talk about some things here. First thing, does that tangent line perfectly represent the change from P to Q along the curve? What do you think? No. Is this exactly the same as that? No. Clearly not. One of these things is a tangent line. And one is the actual curve. And there's a difference between the height of the tangent line and the height of the curve. This is what the differential does. Watch carefully what this does. There's certainly a change in height from P to Q. Do you guys see what I'm talking about? The change in height from P to Q is this entire thing. Nod your head if you understand that. That's the change in height. This is what we call the delta y, the increment along the y-axis, the literal change in height. Along the x-axis, this would be the increment. Just delta x, how much is changing? So this whole thing right here is called delta y. That's the increment of y. Okay, so wait a minute. We just had this idea that the height between P and Q is different than the height between where P is here and where the tangent line is here. This distance between here and here, that little distance there between the height of the point P and the height of the tangent line at x plus delta x. So here, that little distance, that's what we define to be dy. That's the differential of y. There's a difference between delta y and dy. So if you've never heard of a differential, this is what a differential means. That's what a differential means. dy, we consider that to be the differential. I'm going to write a couple things out just so we have this in words. I'm going to write it out. It's probably going to make a little more sense, and then I'll explain it like a 20-second recap, and we'll go from there. So here's what I'd like you to write. Delta y gives the change in height from the point P to the point Q. This total change in height, that's what delta y is. That's it. That's the increment. How much it changes point to point. That's what we're doing. Or, if you want to think about it this way, listen carefully. It gives the total change in height from P to Q, yeah. Or from x to x plus delta x. You guys see that that's the same relationship there. If I'm going from P to Q, I'm going along the x-axis from x to x plus delta x. Head nod if you're with me on that one. That's what this is doing. The delta y measures the height at that point compared to where we started. That's it. Okay, how is that different from dy? Well, what dy does and what dy doesn't do. dy doesn't measure the actual height. That's a function thing. That's a literal change in y thing. What dy does, it measures the change in height from P to a point on the tangent line above x plus delta x. That's what it's doing. So delta y, the whole height. dy, the height up to the tangent line. Do you guys see the difference in that? That's what I'm trying to get you to understand here. So dy gives the change in height from P to a point on the tangent line at x plus delta x. Do you guys have that written down? I don't want to talk at you as you're writing. I want to make sure you're fully with me. Because we're doing just a little bit of a recap, not much. The idea is, it's not super complicated, but it's a little weird the first time you see it. It's like, what are you talking about? I want you to know right now there's a difference between actual change in height and the differential change in height. One of them, what this is doing, this is comparing the change in height to the tangent line, the change in height along the tangent line. That's what it's doing. It's comparing a curve to a tangent line at a specific point. P is the point where we want our tangent line. We're always moving Q to P, okay? We're always trying to find the tangent line to P. So if we say, look at this picture here, we got a curve, we got a tangent line at P. What's going on is and this is an extremely expanded view, okay? This is super blown up. It's teeny tiny when we're talking about calculus. Because delta x, we know it's going to go to 0. So things will be really close. So it's a really expanded picture. We say, now let's check it out. Is the tangent line perfectly representing the curve? Well, no. There's going to be some difference there. So this tangent line at P, yeah, it shoots out this way. It's a line. The curve does this. There's going to be an actual change in height. That's what delta y means. It's the increment. It's how much the height changes literally from P to Q, or from the x coordinate to x plus a little bit, x plus delta x. Now, if you're okay with that one. Now, there's also something else going on. That tangent line is going to be somewhere between there. Right? So that tangent line says, well, we'll now consider the height between P and that point. So same vertical line here. point right above x plus delta x. So the change in height from P to a point on the tangent line right above x plus delta x. That right there, that's what the differential does. That compares the height, the actual change in height, so the actual curve to the height above the tangent line. It compares the curve to the tangent line. Show of hands if you understand the picture behind that. Now there's a couple of the comments I want to make. That's it. That's what a differential is. I've just defined the differential. Now we're going to work with it, but that's what the differential does. That's what it is. I'll give you some workings, some heavier workings here after one more little definition. Now I want you to think about this. Is there a difference, and please focus here, is there a difference between here, when I compare the difference between P and Q, and here? Is there a difference along the x-axis? No. Well, what that means is that if we want to consider, so that there's no change when we talk about dx and delta x, there's no change along the axis of the independent variable. I'm saying that very specifically because when we get to the Calc 3 part of it, we're going to talk about that, about how when we move along the axes of the independent variables, dx, it's going to be dx and delta x are exactly the same. I'll say that one more time. Yeah, there's change, there's a difference between here and the tangent line. There's a difference there along the axis of the dependent variable. It's different. But independent variable, if I want to go from P to Q, or I want to go from P to a point on the tangent line above here, I'm traveling along the x-axis, the exact same difference. Does that make sense? So, dx, okay, now listen carefully. If you understand the d and the delta y, here's what it says. It says dx is the distance traveled from here to here. The d part has to do with the tangent line. The differential part has to do with the tangent line. So the dx is how far you travel from here to here along the x-axis. How far is it?
X plus delta.
How far is it? It's not x plus delta x because we started at x. How far is it? It's delta x. It literally just says it to you. Or you can think about it this way. Dx says how far do you travel from here to here along the x. Delta x is how far you travel from here to here along the x. Did you catch a shift? Deltas are on the curve. D's are on the tangent. It says, well, those are the same. Why? Because it's your independent variable. You're literally traveling along that the same distance and comparing the height changes along the dependent variable. And I have to listen to that in your head a couple of times, okay? This independent variable, this is how far you're changing, and the dependent variable, I know I'm trying to pound in your head because we get to Calc 3 stuff, it's important. The dependent variable responds by changing. Responds, and therefore there's a difference between the actual curve and the height of the tangent line to that curve. In Calc 3, it's going to be a surface. But right now, we're talking about a curve. Okay, all that's to say that these two things are equal. That's all I'm saying. How far do you travel from here to here along the x? Delta x, done. Same vertical lines. Okay, that probably made it. Probably just overtalked that one a little bit, but you know me, so I'm sorry. Just want to make sure you understand it. So dx and delta x, they're exactly the same. There's no error traveling from here or here as far as our independent variable is concerned, so if you understand the concept, that's important. That's an important one. Now how about this? Man, ruin it. Ruin the suspense. Goodness. Is that true? That's clearly not true, all right? Yeah, that's not equal. There is going to be some difference. In fact, what all of calculus does, calculus uses this measurement to approximate that measurement. It's not the same. But, what happens when delta x is super small? I mean, really small, like super small. What happens when delta x is really small? Does this change? Does delta y get closer to delta x? Sorry, dy get closer to delta x or further away? As I move this down, I can't do. Let's see if I can do it. Oh, that's pretty cool. To move this down, the dy gets really close to the differential approaches the increment. It's virtually the same as we get really close. Is it exactly the same? No, it's an approximation, but it's so close. Think really, I'm not talking like here, okay? I'm talking like you can't see it. You can't measure it close. It's so close that the difference is negligible. So close that we treat them as the same. That's the definition of how derivatives work. You can't prove it. Okay, I can prove this stuff where it comes from, but you can't prove that we take the derivative to mean the slope of the tangent line. That is a definition. That's what we call it. That's where it comes from. Now, does it work? Yes. And it's very, very close, but technically it's still an approximation. It's just such a good one, we take it to be fact. That's what happens. Okay, so when we have this, so you can prove things about the definition of the derivative, but when we define it to be the slope of the tangent line, that is an actual definition. I want to clear that up. Some people comment and say, you can't prove it. Yeah, you're right. I can't prove that we call a derivative the slope of the tangent line, but that's what we're talking about here. So these two things make sense, right? Is this equal? No, but as delta x gets really small, that's read really, 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 really small. Or we've been through calculus, so as it approaches zero, as the difference between these 2 points, x, y, speaking, becomes 0, then we have this. Then delta y is approximated by dy. That should look pretty familiar. Does that look familiar to you? Are you guys okay with that idea? That as this idea that as delta x gets really small, the tangent, the distance between the points gets really close, and the secant line, if you will, starts looking like a tangent line. That's the plan. But differential speaking, we're saying the change in the heights and the change in the height at the tangent gets really, really close. That is the idea of a differential. It's comparing the height of the curve to the height of the tangent line over a set distance and then closing that distance. So they're getting really close. Should finish you okay with that? All right, cool. Now, let's come up with a definition. I'm going to do this a different way. I kind of thought of it the other day. I thought this is pretty good way to explain this. Let me talk about something for a second. Yeah? No? Yeah, okay. Yeah. Slope is rise over run, for sure. Now let's go back to our calculus days here. Can you all in this classroom tell me what's the run? Wait, it's what now? Okay, so I like the way you said that. It's x plus delta x minus x. You can answer. What is x plus delta x minus x? Should make sense if that's x and then that's x plus delta x. The difference between them is delta x. Okay. So wait a second though. So there's no change though between delta x and dx. Are you with me on that one? So even though our slope is, I'm going to do this. We're going to kind of do one little substitution every single time. Okay. So we have rise, whatever that is, compared to the run, which is delta x, but I can make that rise over dx. Are you clear on what I'm talking about? Now let's do this. Let's talk about the rise. That was the run. That's the dx. Same thing as delta x. Let's talk about the rise. Which rise? The one that relates to the height of the tangent line. We're talking about the differential. We're using the height of the tangent to approximate. That's what this is all about. Using the height of the tangent to approximate the height of the curve. It's a really good approximation when that thing gets close. That's what we're talking about here. We're always talking about the dy now, not delta y, dy. So what's the rise? What's the rise from P to the point on the tangent line? You all know it. Say it. It's obvious. What is it? Dy. Delta y? No, that would be the actual height, and we can't do it because it's not even a line. We can't talk about slope if we don't have a line. That's why we have this stuff. So we can talk about slope and height and rise and run. That's what we do. So we go, okay, well, now slope is, what was it?
UI.
That's the height. That is the height from P to a point above x plus delta x of the tangent line. And now if you look down that one. Now wait a second. This is where we get to use definition. What in the world is the slope of the tangent line? What do we define? I just said it. What do we define to be the slope of the tangent line at a point? What is it? Everyone in class should know it.
Derivative.
A derivative. What derivative? Of whatever the function it is. Yeah, whatever the function is of the independent variable. Slope is a first derivative. Practically speaking, we've kind of just sort of proved calculus a little bit. Basically, said, yeah, you know what? This is the tangent line. We said let's make a tangent line. This is the change in height. This is change in run. It's a rise over run, and we called that a derivative. That's literally what it means. What's a differential do? Well, the differential has a different take. Differential says, what if I solved for the rise? So basically, get rid of the fraction. Does that make sense? Mathematically, it's legal. We just multiply by a denominator. As long as the denominator is not zero, it's approaching zero, but it's not zero. We can still do it. So we go, okay, well, does that... Oh, I forgot my E. Sorry. Does that make sense? Does it make sense the rise should be the rate at which we're rising, rate of change, slope, times the amount I let it rise? A fraction times how far I let it go is going to give me a proportion of that. It's going to give me my rise. That's exactly what we're talking about. Let's do it here. Let's multiply both sides by dx. Can I do it? Yes, because dx is literally just this change. It's a number, and it's not zero. It's approaching zero, but it's not zero. And what we end up getting is dy equals... So excited. dy equals the first derivative of x dx. Here's what I want to know. Does it make sense about where that actually comes from based on the picture and based on this little proof that we get? Are you sure? Can you see the slope working for you in the first derivative and how it relates to the differential? Differential of y is the height up to the tangent line. That's all it is. That's all it is. This is a differential. This is what a differential is in one variable. Y is the dependent, x is the independent. That's what a differential is. That's it. Done. That's Calc 1. Do you understand where a differential comes from? We take, I don't want to re-explain it, but we get tangent line, change in height total, that's increment, change in height through the tangent, that's a differential. We relate it to the slope of the tangent line and the run. That's it. It's not a super complicated idea, but it's an important idea. Do you truly understand it? Are you ready to make the jump to the Calc 3 stuff? I need to leave that on the board because we're definitely going to use it. We're going to use it twice. So the Calc 3 stuff. Now, let's transition a little bit. All I need to know, you understand? You understand? I almost said you understand it. Did you understand this proof? I can speak like that. Spent some time in the South. I need all of this right there, and I need this little statement. So from all this, we got the punchline of that. That was the idea. This is what I want. That's what we need to know. Now we talk about 3D. So let's transition a little bit to R3. Everyone, right now in class, in 2D we have curves. In 3D we have... So, we're going to hopefully draw a nice, pretty picture here. hoping you can see the surface I'm trying to create. Here's what I want to show you. Now that we're talking about surfaces in R3, how many independent variables do we have in R3? 1? No. 2? Are you? Oh, good. Crap. Okay. Remember surfaces, right?
Yeah.
Surfaces have 3 total variables in R3 and 2 independent. What are the independent variables here? So we plug in an x and a y, we get out a z. Z is the dependent, x and y are the independent. Are you following what I'm talking about? You need to know that. Is that an adequate picture? I know you can't even see it from too close. Can you tell the surface that I'm trying to draw? Can you see that surface? Here's the deal. In R2, we've got curves, we got tangent lines. In R3, we don't have curves anymore until we have vector functions. We're not talking about that. We're talking about the surface right now. In surfaces, we don't have tangent lines per se until we start restricting our vectors, until we start restricting a direction. We're not there. That's in 13.6. That's in a couple sections. We're not there yet. So right now we're going to talk about this. What if I have a surface? I didn't bring Happy. I don't have a balloon. I don't want to take time blowing up. So if I had a surface and I lay something on it, I have this awkward thing of, if I have a surface and try to lay a line on it, I have a whole bunch of ways to do that. But if I have a surface and I try to lay a plane on it, there's only one way to do that. So we're going to consider surfaces and tangent planes right now. That's what differentials have to do with in 3D, in R3, with surfaces. It's the difference in height between 2 points on the surface and a point on the tangent plane. That's what's happening here. So I'm going to illustrate this a little bit. I want to make sure that you guys are okay with it. We're going to start at P, and just like we did here, had a tangent line at P, I want to consider a tangent plane at P. Are you with me? I want the tangent plane at P. Kind of hard to draw. I'm going to do my best. Let's imagine that's there. Yeah. Let's make that small. Close enough. Does that look good to you? I'm not the best artist, but can you see the representation I'm trying to create? I've got a surface like this, and I've got my tangent plane. What's the plane tangent to? Is it tangent at the point P or at the point Q?
Point P.
Can you see it? I'm trying to lay this plane right under this surface. Just like this. So it's only touching the surface at one point, and it's going out. Is that now? This is kind of an obvious question. It should be an obvious answer. Is this plane perfectly representing the surface? Does it perfectly go along with the surface? No, surfaces change, planes don't change. That's the nature. Lines don't change, curves do change. That's the nature of these things. So what we're going to be doing here, the way the differential works for surfaces, is I'm going to be comparing the height between P and Q and the height between P and whatever that point is. So let's illustrate this a little bit. Every single point like ever has an ordered pair to it. So the point that gives us P, let's call that XY. Now here's the issue. I'm going to try to kind of flesh this thing out for you. When I changed from here to here, there was only one variable that needed to change from here to here, and the Y responded by changing. The Y responded here. So X was the only variable that changed. To move from here to here, I just had to add delta X. Head nod if you're with me on that one. Come on, people, I need your attention. I need you to really get this stuff, okay? So we move from here to here by adding delta X. How do I move from here? From here, let's go to this. How do I move from here to here? Well, that means I've got to move on the XY plane, the plane of my independent variables. I've got to move from here to here. What must I do? Do I change just the X? If I change just the X, that's just this one. Not this one. That's not along the X. Just this one. So I do have that. I do change the X. Let's call that delta X. That change is delta X. Are you following me?
Yes.
What else do I have to change?
Y.
Delta Y. Yeah, that's right. Y is also an independent variable now. Which means at this point is X plus delta X, Y plus delta Y. Did you get that written down? Do you understand the picture? It says if I want to move from P to Q, I got to move down here first. I have to find where XY is for P. Then I got to add a little bit to it along the Y. Got to add a little bit to it along the X as delta X and delta Y. And it gives me this new point projected on the XY plane from where I get the height at Q. Show of hands, feel okay, for real. So here's what we're doing. I'm going to write this out so you have some good notes on it. Number one, we have a surface from P to Q, and we're taking a tangent plane at the point P. So given a surface from P to Q and a tangent plane at P, here's now the representation of the differential. Watch carefully. I don't want you to miss it. Please look. Please look. Please look. Is there a change in height? By the way, what variable represents our height here? Come on. What variable?
Z.
Perfect. Is there a change in height in the change of Z from P to Q? Is there a change in height?
Yes.
Is there a change in height from the point P to a point on the tangent plane right under Q or right above this? Yes. Just like there's a change in height here and a change in height here, a change in height between the points and a change in height between the point and the tangent. There's a change in height between P and Q, a change in height between P and the point on the tangent. If I just draw a direct, and my graph's not to scale because I'm not perfect, so you're going to have to kind of use your imagination. But if I drew this level, if I made this level at Z, and I drew it all the way over, let's pretend it intersected right there. Let's say that's the height at P. Does that make sense? That's the Z of P. Here's what differentials mean now. The complete change in height, let's use what you know. The complete change in height from P, the height of P to the height at Q, or the height from XY to the height at X plus delta X, Y plus delta Y. The height between those points is what? Is it a delta or is it a D? Which one? It's the whole thing. It's the delta. Delta what?
Z.
You can't use Y. It's independent. That's the delta Z. And now if you're okay with that one. For real. Yeah. What's that little bitty height? That right there is what the differential in 3D, R3 surfaces, that's what it represents. I'm going to write that out for you so that you know. Delta Z is the actual change in height from P to Q. It's the actual change in height from xy to x plus delta x, y plus delta y. That's what that means. Write that down, okay? Delta Z is the actual change from P to Q. Or from the point of the xy plane to that point of the xy plane, which is what gives us the heights of P and Q. DZ is not that. Can you see that? I don't want to waste your time by doing this. Can you see the relationship between this and this? Can you see the similarity between these two things? We've got a curve and a tangent. Total height between the 2 points. Height between the point and the tangent. We've got a surface and a tangent plane. We've got total change in height. That's the delta Z. That's the change between these 2 points. As I'm moving, I don't have one axis anymore. I have 2 axes. I got to move along both of them. The change in height of the function between here and here. That's the total change in height between the point and the other point on the surface. That's what delta Z means. The DZ is the same thing as here. It's the change in height between the point and the point on the tangent. Only this time, we've got a plane and not a line. You with me? And it takes these 2 things to get there. So that's what DZ does. It's the change in height from P to a point on the tangent above x plus, above this point. That's what it is. That's the differential in 3D. Now, here's my next questions to you. You should get it. You should get it. You ready? What we said was that to get from here to here along the x, to get from here to here, that's called dx. The change in, we called it run. The change in run from the point to the point of the tangent line along the x-axis was dx, but it was the same thing as delta x. They had to be exactly the same. Do you follow me on what I'm talking about? Now, for here, I got to let 2 things change. I have this change in x. Yes. Is the dx still going to be equal to the delta x? Is it still going to be equal?
Yes.
How about the dy? Is the dy going to be equal to delta y?
Yes.
When I'm moving along the axes of the independent variables, I'm moving from, okay, well, you know what? Let's do it. Let's do it. You ready? Here we go. I want to move from here to here. That's what that represents. I want to move from here to here. The change in x and the change in y are dx and dy just like they were from here to here. It was a dx. How far do I have to move? Look at the board. Now, I don't want you, if you blink, you're going to miss it. Don't miss it. How far do I have to move along the x-axis from here to here? That's on the tangent plane. I know they're close. But from P to the point on the tangent plane, how far am I moving in the x direction? How far?
Delta X.
Delta x. How about in the y direction?
Delta Y.
Delta y. So how the change in x along from here to here is delta x. There's no change. There's no difference between them, I should say. As far as the independent variables are concerned, that's the point I was trying to draw, is that independent variables, there's no error there. That's cool. It's the height of the dependent variable that the differential compares. That's what we're doing. So for us, we go, okay, since x and y are both independent variables, you might want to write a little note there. Make sure I got independent right on this one. Something we get confused like, wait a minute, I thought you said delta y was about, not equal. Well, that's because y here is the dependent. Y here is not. They're both independent variables. The measurement of the height, that's a z measurement now. That's what we're considering. Okay, I'm going to have to race this side of the board because I need this to prove the rest of it, but I want to make sure that you guys are literally okay with this. The idea is really kind of strange first time you see it. There's a couple main questions I want to ask you. Number one, do you see the similarity in using this technique to get this thing? Do you see the similarity for real? Are you understanding it? Am I killing you with boredom? No. Sorry. Yeah. Would you rather me just give you formulas and crush them? No. That killed me as a student. I hated that. I really did. Like, where's it coming from? Just do it. All right, I could cut this class in half. You can understand crap about it, but I could cut this class in half. We could do that. Save me a lot of time. But if I'm going to go through the trouble of doing proofs, I'd like you to reasonably pay attention. If you don't get it, ask questions. If not, if you don't want to do proofs and stuff, then we'll just burn through. I'll crush some derivatives. We'll go home. Well, you can do that too, but you don't get candy for it. Anyway, that's the whole main thing. Increment, differential, height of between the function and height between the function and a tangent something. That's the whole idea of differentials. Now, the idea of the proof. I'm going to erase this thing and redraw the surface. I want to give you the idea of how this stuff actually works. It's pretty cool. This thing is based all on the Calc 1 idea. It's neat. So we're going to look at it. Because I don't want you just to copy it down, get a formula, and try your best to work at it. You probably can succeed, but you're not going to understand it. So let's create our surface again. Here's P, here's Q. Here's the idea of the proof. So proof, sort of. I like more the idea of the proof. I like you to actually understand. I'm not going to go into the nitty-gritty of it, but I want you to understand the idea of the proof. Here's the idea. Delta Z, let's talk about that. Let's talk about delta Z. We can consider that. Listen carefully to my verbiage, okay? Let's consider that as a sum of the changes along the surface in the x direction and then along the surface in the y direction. Let's consider that. So basically, here's what I'm going to do. I'm going to start here. I want to go along the x direction. That's going to get me part way there. So this I want the change in z, but only along the x direction. Are you following? And then I'm going to go, yeah, and then now let's switch. Wherever this is, as far as now I want to switch and go along the y direction. And if I take these and add them up, that will be my total delta z. So that's what I want to do. I want to go along the x direction for a while. Then I want to go along the y direction, and I want to add those two heights up. You guys get the idea of the proof? So the idea says this is that. Notice I'm not using d's yet. I'm not using them at all. I'm using deltas, which means there's no error in this yet. It's literally the change in height along the y plus the change in height along the x, or vice versa, and we get total change in height. Does that make sense to you? It's a continuous surface. We can do that. So we go along the x-axis, hey, total change in height, and we stop, and we go, okay, along the y. When we get to that point where we're along the y, we add up the height along the y. Total change in height is given by height along the x, height along the y. We get total change in height. Should be okay with that one. Now we have some fun. Here's the cool part about it. If I'm going along the x direction, if I'm just going along the x direction, I am in a plane that is parallel to the what z plane? If I'm in the x direction, I'm parallel to the xz plane. Does that make sense? So if I go along that, go along that, we're parallel to the xz plane. But wait, this is the whole point. This is the cool point. Listen, look, listen and look, and pay attention and learn. Do it all three at once. Okay, is that 4, 3? I don't know. I can't count. So check it out. If I'm talking about the change in height along the x-axis, I'm in a plane parallel to the xz. This should be ringing a bell from last section. This should be there from 13.3. Like, stop and just go in the x direction. Okay, that means I'm in a plane that's parallel. Okay, that means that I've got this curve, not a surface. I'm restricted to a plane. I've got this curve that's solely in the x direction. I've got a curve that's solely going along the x direction. I'm restricted to a plane. Does that make sense? That means we get to use all of this Calc 1 idea. We go, well, wait a minute. Hey, if you're restricted to a freaking plane that's along the x, x is your only independent variable, because you're not excited. This should be exciting. This is differential, it's partial differentials. Well, it is partial differentials. Partial, what do you call those damn things? Derivatives. This is calculus class, right? Okay, good. If we're I'm getting excited about it because it's freaking cool, but if I restrict you to a direction, x direction, we're in a plane, we create that plane, creates a curve on the surface. Not a surface anymore, it's just a curve. And we go, wait, if I'm restricted to the x, x is my only independent variable. Why? I don't care, it's held constant. That's why y is equal to a constant, we're in that plane. We go, well, then what is this? I don't know, but I could tell you something. I could tell you that it's about equal to this. Did you catch it? Look right here if you didn't. Right here if you didn't. Delta y is not equal to dy. That's the dependent variable. Delta z along the x direction is not equal to dz along the x direction. That is your dependent variable. You follow? But it's close when I let this go to 0. But that's close when I let, I erased it. When I let the delta x and delta y go to 0. Did you catch it? When I let them go to 0. Okay, but wait, what's this thing? True or false? This situation along the x direction is two-dimensional. True or false? True. If I'm restricted to a plane, which I am, it must be two-dimensional. Which means that my, oh come on, put it together. What's my independent variable? Everybody, what's my independent variable? What's my dependent variable? Not y. Y is held constant here. It's nothing. Then I get to use that. So delta dz with x is the first derivative. Yeah, it's the first derivative. It's the slope. But it's only with respect to, come on, if you get this, I know you get it. It's only with respect to, it can't be with respect to z. That's a dependent variable. It's held along the x direction. It's with respect to x. D, whatever your independent variable is in that direction. dx. Do you see that that's the same approximation that we have used right there? Do you see that that's the same approximation? Do you see that if I'm held to the x direction only, that this, the differential, it's this, guys. I don't want to get, it's going to get too cramped if I try drawing everything, but watch. That's in a plane, right? That means it's a curve. That's literally the situation. If I draw the tangent line, it's on a plane. If I draw the tangent line, there's a change, there's a difference between the delta z and the dz of x. But that difference right there is that. It's the same thing. It says, oh yeah, but that thing I defined to be, slope times run. Slope times run. That's delta x, that's dx. That's where we get it from. Does it make sense? It's pretty cool. It's pretty cool. But now the same thing happens here. I go, okay, well, what about delta y? Well, delta y, sorry, I know it's really small, but that says dz sub y. There is a difference between the increment and the differential. So I'm a math teacher. You didn't get that one. 0 coordination. I can hit volleyballs? Goodness. That's how I met my wife. Did I tell you that story?
Yeah, you did.
I did?
Yeah.
I smashed her right in the face.
Yeah.
She was always on my team after that. Booyah. Yeah. Got married. See? What was I talking about?
It's easy.
No, it's volleyball, obviously. Weren't you listening? Anyway, that's the actual change in increment. That's the differential. But wait, if I want to approximate the increment, you go, wait, can I do it? Yeah, of course I can do it. Because if I restrict my motion to just along the y direction, I'm not going to rewrite that, but just along the y direction, we're in a plane that's parallel to the yz plane. We create this plane. The plane has this curve along our surface. The curve is in a plane. It's two-dimensionally. Only you got to tell me this. What is my independent variable if I'm only along the y direction? And x is constant. And what's my dependent? Perfect. We have this situation again. We go, okay, well, then this is approximated by dz along the y. Yes, the increment is approximated by the height between this point and the point on the tangent. That's it. And that's equal to the slope in the y direction times how far I travel in the y direction. That's delta y. But we know that delta y is the same thing as dy. Do you guys agree that this is the differential in the x direction, that's the differential in the y direction? Are you sure? If I add them together? This thing here is certainly equal to this. Look, equal, not approximated. This is equal. This is actual change. You guys see the increment? The actual change. Actual change along the x, actual change along the y is actual change along the x direction, plus actual change along the y direction is total change in between the 2 points. That's what that says. However, that is approximated by this. That is approximated by this. So if I drop these down, it now becomes an approximation but we know what this is. This guy is this guy is this guy is this. So we know these two things, if you follow along, are these two things. This right, sorry. You can stop me when you see things like that. It's okay.
We assume you're right.
You just assume that I'm right? That's a really bad assumption to make sometimes. I usually say the right thing, but sometimes it comes out weird. Then right here, the differential along the x plus the differential along the y, this is what we call the total differential. Listen, we just spent a whole long time proving this for only one reason, so that you would understand it. You could probably have fast forwarded this lesson like an hour, and I get it. I get some of you don't want to understand the concept behind it. You just want to be able to do it. And that's okay. Then skip to right here and just focus in on this, okay? Here's what you need to know in total for the situation. You need to know that any delta is actual change. So this delta z is the actual change in height from here to here. Do you understand that? It's approximated by dz. It's approximated. Is it a good approximation? Oh yeah. If we let these points get really close, the change between the tangent plane and the surface are real small. Just like here, just like if you let this go down. The change between delta and the d is really close. You with me? That's the idea here. That's what we're doing. So it's approximated by this. How do we do it? We hold the surface in one direction. This is slope, and I need you to get it. This is slope times run. It's giving us rise. This is slope times run. They're literal lines. They're literal lines in 2 dimensions because I'm restricting to the x, and I'm restricting to the y, and I'm adding those up. Slope times run plus slope times run gives me 2 heights. I add the heights together. I get the change in heights from the slope line, the slope of the tangent lines, held constant in planes. That gives me a real good approximation for the change in height between 2 points. I don't know. Do you understand the concept behind it? For real, like honestly, do you get it?
Yeah.
Now, how we do it, honestly, it probably couldn't be easier. Can you do it? You know what that means? Do you know what that means? What does that mean? Oh yeah, holds in the next direction, hold y constant. How do you do a partial derivative? Hold y constant. Can you do that partial derivative?
Yeah.
Can you put the letters dx and dy next to them? Done. Let's do one example. We'll take our break. I need it to sink in right now, okay? So we're going to do this and then take a break. Any questions before I erase any of this? It took me a long time to do this. Did this help with Calc 1 differentials? Was that useful to you? Have you ever... Did that help you at all? Okay. Thanks for the enthusiastic response on that one, guys.
No problem.
Yeah.
I'm trying to remember back.
Well, I just taught it to you, so you don't have to.
Yeah.
That's why I said, did you appreciate it? You should be, yeah.
Yeah.
Yeah, Leonard. It's awesome. Thanks, man. No problem. Looking out for you guys. Love having a conversation with myself. Thanks. Okay, let's do it. This is going to be about a maybe 20-second problem. Well, as long as you can take derivatives. Here's what differentials do. So I'm not joking. It's as easy as this. It says, I want you to find the differential of z when z equals this equation. The differential of z, I just proved it, is the partial derivative of f with respect to x, dx, plus the partial derivative of f with respect to y, dy. Done. So let's try it. Let's put it together. Or you could use this too. If you prefer the z notation, you can do this. Might make it easier. I don't care what you do. Can you take the partial derivative of z with respect to x? Yes or no?
Yes.
Okay, so we would clearly have what rule for with respect to x? Every time chain rule. So what we get with chain rule is, and listen, I'm going to do them fast, all right? I got to trust that you're okay on these things. I don't have time to hold your hand with derivatives in this class. Outside of class, sure, but not inside of class. We're going to crush them. So with respect to x, we're going to get 2x y e to the x squared minus y squared. That's the partial derivative of f, or z, with respect to x. Make sense? What is it? It's the slope. It's the slope if I restrict the surface in one direction, along the x direction, along that plane, and I take a tangent line to that curve that intersects the surface on that plane. That's what I'm doing. With respect to y, what do I need? Product rule and? You can check my work on that one if you would. I'd appreciate it.
It should be plus. Shouldn't it? Minus. Like, it would be two negatives.
Product rule is always plus. So derivative of the first times the second plus.
Wait, oh, product. I was thinking, yeah.
Oh wow, no, that's not right. Yeah, pretty sure. You guys okay with partial derivatives? So how do we do a differential? One step. This is the differential. The differential of z is now, we take this guy dx plus this guy dy. Done. That is what a differential is. Can you do it?
Yes.
What's it mean? Because don't do it without knowing what it means. What's it mean? What's that mean? What's this mean? Change in height. Total change in height. What's this mean?
An approximation.
An approximation of the change in height. This is an approximation in the change of height between any 2 points. Between any 2 points. That's what it does. What it's doing, it's using a tangent plane to approximate change in height. That's what a differential does. Cool, huh? That's what it's doing. How this and this work, I'm going to show you what we get to do with those things when we come back. Maybe just one. All right, so like I said, quick examples. I gave this to you to practice during the time here. So here we go. I want to find a couple differentials, just here and here. How we find differentials is very, very straightforward. It says take the partial derivative with respect to however many independent variables you have and add them up with d, whatever your independent variable is. So in our case, we've got 1, 2, 3. We're going to have to find 3 partial derivatives. So in our case here, the differential of w is the x dx, partial derivative with respect to y dy, partial derivative with respect to z dz. That's what we're looking to get. So we got to take these 3 partials and then just jam them together with addition. And now if you see where that's coming from, that's why we learn this stuff. It can be extrapolated for more variables. So partial derivative with respect to x. Again, we're going to go quickly. This is 2x e to the y. What happens here? 0. With y, we got, let's see, x squared e to the y plus ln z. Can you follow that one?
Yep.
Derivative here is e to the y with respect to y. Here we got ln z partial derivative with respect to z is 0 and then y over z. Because we have that ln z, so over z times our y, we get y over z. Head nod if you're okay with that stuff. Now, is that the differential? Well, no. It's the parts of the differential. It's the partial derivatives. We jam them together. And we got that our differential is partial with respect to x dx, partial with respect to y. If you're one of those people who don't like parentheses, shame on you. You got to have them. Partial derivative with respect to z, dz. That's it. That's what a differential does. What I'd like to do, I'd like to give you just a minute to start that. I want to see at least the setup. I want to see how many partial derivatives you need. I want to see what the differential of f is going to look like. And then I want you starting to work on the partial derivatives. So let's just do the setup. I'm only going to give you about a minute to start it, but start the setup on that problem, please. Okay, I'm going to get you started here. How many independent variables do we have? So we need three partials, x, y, and z. We need a dx, dy, dz. So this thing's going to look like partial derivative with respect to x dx, then one with y dy, then z dz. That's all there is to it. That is what a differential does. It describes the change in height. This is 4D, but change in height from one point to another. It approximates that change quickly and easily, and it's a good approximation if your changes are small. If the changes are small, that's what we're trying to do here. So let's try that. Were you able to find the partial derivative of f with respect to x? Were you able to do it? Yeah or no?
Yes.
Hopefully you got 2 over 2x minus y for the first part. Here, partial derivative of this with respect to x says chain rule. You get 2z, and then you get your exponential back. Did you guys get that one?
Yes.
Hope so. Partial derivative of f with respect to y, very similar. We got chain rule, derivative of this with respect to y is, love it. Partial derivative of f with respect to z. I told you I'm moving fast. I do need you to be able to do these on your own, but I got to move quickly on this stuff. We're kind of running out of time. This with respect to z is what?
0.
This with respect to z is 2x by the chain rule times e to the 2xz. And not if you can at least follow it. Yeah or no? Is that our differential? It's close. It's the parts of it. So we get this whole piece, the partial dx plus another partial with respect to y dy plus the last partial with respect to z dz. Can I have a double check on my work? Did you guys get the same thing that I got?
Yes.
Now, how do we even use it? So we're doing this stuff, but how can we use it? This is a stepping stone. So this is, I'm just going to give you some numbers and show you how to plug them in. Then we're going to do a few examples that illustrate why this is actually important, why we do this stuff. So first one, can you approximate the change Can you, watch carefully, it's not hard, but you need to know where everything's coming from, okay? Can you approximate the change? That would be approximate delta F, the actual change. Hey, everyone in class right now, what approximates delta F? What approximates the increment? The differential? What's the differential of delta F? Yeah. So this is going to be approximated by df. Oh, hey, look at that. We got a formula for df. Look, this can't just be a formula. This allows you to plug stuff in. Let's approximate that change. I'll tell you one thing. The less it changes, the more close our approximation is. The more it changes, the less close it is. So let's see if we can do this. Do you have an x, a y, and a z? A starting point. What's your starting point? So x is 2, y is 3, z is 0. And now that you understand that. Now, do you have a change in the x?
Yes.
How much?
0.01.
0.01, positive or negative? That means listen carefully to the verbiage here. The delta x would be 0.01. Clear? But dx is the same as delta x. That means that if I have a delta x of 0.01, I can use it for my dx. That's what that means. It is the change in x. That's all it is. It's going to approximate the change in the function, the change in height. So our dx is 0.01. Can you tell me what the dy is and be careful on it, please? Say what?
Negative 0.00.
Negative, because it's dropping. And the dz, what's the dz?
0.04.
So here's the cool thing about it. If we want to approximate the change of this function from this point to this point, we take these numbers, plug in for x, y, z, dx, dy, and dz, and it will give us an approximate change. How close? Pretty close. Could it be better? Yeah, if our change is smaller, it's better. So let's try. So what we get, I got 2 times 2 minus 3, z 0, so this is gone. This term is gone. dx still matters though. 1 over 2 times 2 minus 3. dy is negative. Then I got 2 times 2 e to the z is 0, so that's 0. I want you to take just a moment to look at it, see that you see where all those numbers are coming from. Can you follow that, where those numbers are coming from? If you can't, just take a moment later on, verify that all of these pieces are just all these numbers going into all those spots in the appropriate spot. What we get out of it, what the approximate change is, what this equals about 0.21. That means the delta F, the approximate change, is about that. Is it exactly? No, it's not exactly, but it's pretty close. Can I just get a show of hands if you feel okay with doing this process? Is it super hard for you? I need to know. For me, for me, I've been doing it for a while. So for me, I'm like, okay, it makes sense. But I need to make sure that it makes sense for you guys. Does it make sense for you guys?
Yeah.
Let's step it up a little bit. I want to do 3 actual real examples, stuff from like not just functions. I want to deal with real stuff. So let's talk about pressure and gas. Now I'm full of hot air, so this should make sense for me. But if you have any sort of science background, you know that if I increase the volume with a gas, I'm going to decrease the pressure. And if I decrease the volume, I'm going to increase the pressure. That's inverse relationship. If I increase the temperature, it's going to increase the pressure. If I decrease the temperature, it's going to decrease. That's a direct relationship. So for a certain gas, we can model the pressure. Isn't it pascals? Is that right for pressure?
Yes.
By this. So pascals related 8.314 temperature in Kelvin over volume, and let's say in liters. So let's find, right now, I want to see if you can do it, find the differential of the pressure. What's it going to let us do? It's going to let us approximate the pressure for any given change. What are my 2 independent variables here? So I need to find 2 partial derivatives, just 2, with respect to v and t. If v is the variable and t is the constant, I bring it up, have -1, multiply by -1, drop the 2, we're good. If t is the independent variable, this is even nicer. Done. Those are the partial derivatives. Head nod if you're okay with the partial derivatives. Let's write out the differential. So it should be partial of v dv, partial of t dt. So far, so good? Guys in the back left? Yeah, no? Jason? Guys over here? Now, let's see if you can fill this out with some real life stuff. Let's say that our volume goes from 20 liters to 20.2 liters. Our temperature goes from 300K to 250K. Can you approximate the change in pressure? Let's outline the things you know right now. So list out all the stuff you know based on this information. Go for it. When you do the variables themselves, it's always the starting value because we're trying to approximate from that starting spot. Okay, so when we talk about the V is where the volume starts, not where the volume ends. Where the volume ends has a change in V associated with it, a dV. So our volume starts at what, please? What's our temperature start at?
300 Kelvin.
Now, did you catch that? Yes, no? What else do we know? I can't hear you guys.
dv and dt.
What's our dV?
0.2 positive.
What's our dt?
-0.5.
Perfect. Can we approximate the change? Well, we've got everything. We've got the volume where we started, the temperature where we started, the volume where we started. We have how the volume changed. We have how the temperature changed. That's the idea, how much it changed. So when we approximate the pressure, the actual change in pressure, that's what that means, the actual change. It's approximated by the differential. That differential says, well, we can plug this in. You don't need to pull your calculators out, I've already done it. I just want to make sure that you guys have the correct numbers in the correct spots. Do you have the correct numbers in the correct spots? What this gives you, and your units actually match up to where I wrote them, but you got K, you got L squared, you got L, done. You got K, you got L. Temperature over, that is Pascal's, right? Temperature over volume in liters? Pretty sure, hope so.
Yeah.
Otherwise it just blows up in my face and I look like an idiot. Hopefully it is, otherwise good, but I'm going to say it anyway. So our actual pressure is approximated by the differential, which is -3.3256 pascals. It's a drop. It's a net drop in pressure. Now, I always found this sort of like, well, wait a minute. Couldn't you just plug the numbers in and figure out the actual change in pressure? Yeah, pretty sure. Sure you should do that. So why do we do it? First, a lot of times differentials are easier because it gives you one thing to plug in, all said and done, and you're done. It approximates, and if it's a small change, it's pretty good. Plus, it lets you do it for lots of points at a quicker rate. You don't have to plug in 2 different points. You just plug in 1 point and then change, and see how that change affects it. You can model things off of that. Third is for this, and I really like this. I do a lot of things that require measurement. I have a lot of hobbies that I measure things with. I get a micrometer, and because I do a lot of small detailed stuff. Well, the problem with that is that every tool that we make inherently has error in it. Inherently, because the scale that I use, it's like the micrometer, it's like plus or minus 0.001 inches. That's really close, but it's still plus or minus 1,000th of an inch. So whatever measurement I have, it could be off by that much. Plus or minus, that's 2,000ths. You with me on the idea? We can use differentials to give us the maximum error in our total measurement. That, I think, is a pretty cool deal. So I'm going to show you how to do that. So the only thing I want you to know, and I'm not going to write it down because you'll see it in the example, but the error. So if you're using a tool, right, and you're measuring it, that plus or minus 0.1 inches or plus or minus 0.01 grams. I don't know what you have. But those errors are the possible changes in your measurement. It's the possible changes. And we can take the biggest error, put them here, add them together, and get the maximum error possible. And I'll show you how to do maximum percentage error in a minute too. You guys okay with the idea first though? So let's continue. If you weigh an object in air and you weigh an object in water, and you put them in this following ratio, it gives something called a specific gravity. So we're going to talk about specific gravity. So specific gravity is the weight of an object in air divided by the weight of the object in air minus the weight of the object in water. While I'm writing out the rest of the problem, I want you to find the differential right now. Were you successful in finding the differential? Were you able to do that? Did you try?
Yeah.
Yes.
You need to try these things. Remember talking about the guided practice thing?
Yeah.
Talked about it. You gotta try them. Even if you function it all up, okay? It's okay. But you've gotta try it. I'll give you 10 seconds. Try it. Do something. Just do something. Just draw kitty cats in the paper on it. What are your two independent variables?
A and W.
The partial derivative with respect to A, oh goodness, low d high minus high d low, square the bottom of weight. Well, I know it's going to be squared down here. What's on the numerator? Did you find it?
Negative W.
Yeah, that's what I got too. Did you get negative W on the numerator?
Yeah.
Let's see. Okay, plus. So that one, I'd move this up. I'd make that a negative 1. That's a constant, so negative, but then chain rule gives me that negative 1 back again. I think, pretty sure. Can you double check my work?
Sorry.
So that's our differential. Now, what's a differential do? Come on, folks. I need more out of you. What's a differential do?
Shifts us in the function.
Gives us a change in height or function or whatever the function it is, okay? It gives us change in that function. Now, if I tell you, we measured something, and I had the measurements for air and the measurements for water, you now know your A and your W, now that you're okay with that one. But I also know this. I know that my scale is accurate for air to 0.02 pounds and for water to 0.04 pounds. That means that I could be anywhere within that range. The maximum it could be is 0.2 pounds away in either direction. Does that make sense? Or 0.4 pounds away in either direction for water. Actually, with stuff this light, that's actually not that great. That's quite a bit of error percentage-wise for these two measurements. For heavier stuff, that'd be great. For this, that's not that fantastic. Okay, so we're going to get some large error out of this. But here's what to do with that. If our A, well, okay, you tell me, come on, quickly. What is our A?
2.2.
Do you see that it's 2.2 for air? What's our W, please? Our dA. dW is plus or minus 0.4. Here's how to use those. If we want to find maximum error, please watch carefully. Maximum error is going to be the absolute value of the differential. Because I don't want these, if they're negative, I don't want these errors canceling each other out. Does that make sense? I don't want them to do that. So for us, we're gonna find the absolute value of that differential. So I'm gonna plug the numbers in. So negative W over 2.2 minus 1.8. We're going to multiply that by the dA. Listen, if you're talking about the differential of A, the maximum error there, it's either direction 0.02. The absolute value of that is just positive 0.02. It negates that negative. Does that make sense to you? That's what happens. You know what? We'll do it. Yeah, we'll do it that way. Yeah, we got that one. I'm not concerned about your ability to crunch numbers right now, but I'm concerned about your ability to understand what all these things came from. Do you understand where all they came from?
Yeah.
So we get the numbers in the right spot. If you do them on your own, did anybody do that, by the way?
Actually, calculate.
Does anybody do that?
Yeah, I don't know if you did that. Did you? I did it. I wrote it down, but I want to make sure I'm right. I got 0.775 pounds is what I got. 0.775. No?
No, I just accidentally cleared it.
Oh. Dang, that sucks. So if we use those errors that you have in your scales, we can find out the maximum possible values that were off. Now, I do want to show you something. This changes for every weights that we put in there. This is at this one certain weight. It's at this certain weight, we can be off by 0.775 pounds. That's why I said it's not that great. Because if you look at what we weighed, and tell me we could, the specific gravity we get out of this is going to be off by 0.775 pounds. That's kind of crazy. So the specific gravity itself could be off as far as that much, either positive or negative. That's why it's max error, either direction. That was what the absolute values did for us to add those errors together cumulatively. Show of hands if this is understandable for you. Let's do one more. I think this example is really interesting, but before we do that, we got one thing. I do want you to know that we can also find maximum percentage error. Here's what maximum percentage error does instead of maximum error itself. Maximum error itself is going to be in the units that the problem's in. Percentage error is not. Percentage error is going to say something like, hey, your measurement here could be off as much as 5%, 10%, 7%, 20%, whatever that is. That's maximum percentage error. So little side note, how we find maximum percentage error, we take the total change, or sorry, not total change. The total change, but in this case it's the total error. Take the total error and divide it by the actual function value itself. That's going to give you a percentage of the function that is in error. So dividing the change by the total gives you a percentage. That's what we're doing. And we always consider it to be absolute value. You guys okay with that one? So it'll of course be approximated by the df, by the differential. I want to show you how this works in an example, and then we're going to call it good. So I found this one. I think it's pretty cool. maybe you guys who are engineering minded, are there any engineering majors in here? You guys? Good. Wow, that's a lot of you. Now I'm nervous. Should be. Should I be? Tension of a cable hanging at its lowest point is given by that. Well, what's all that mean? Let me draw you a picture. Suppose we have some bridge, some roadway that's supported by two posts with a cable. Here's what this all means. L is the distance between the posts that are holding up a cable. Tension, the tension is going to be this tension on that cable at the lowest hanging point. The A. The A is the distance between the lowest hanging point and the top of that pole. That's what the A is giving you. The W is the weight of the road, path, bridge, whatever, in pounds per foot. So however many pounds are in a foot of that road, that's what that weight is talking about. Now we're going to do some math magic on this thing, but before we do, I want to tell you something. When we do our measurements here, here's what I know. I don't want to give you a measurement like it's plus or minus 4 pounds or plus or minus 2 pounds for the entire road. What I know is this. Based on our past experiences, our weight for the road is plus or minus 1%. So if I have more road, of course I'm going to have a bigger error. Less road, less error. It's 1% all the time, whatever. The error for our length is 2%. So maybe it's a long bridge. I don't know. We're off by that much. And our A is plus or minus 2% as well. So what I know is the percentage error of these measurements is as follows. Those. Do you guys understand the question? You sure? We got this cable, right, hanging over a road, and there's going to be some tension on it. This is going to create a distance. This is going to be a weight, and we're measuring it in pounds per feet, and we got this length that this thing is running. We're trying to find the tension in there. We also want to figure out what's the maximum percentage error of this whole thing. That's what I want to ultimately figure out. So how much of the tension, now is that important as an engineer to know if your measurement's going to be off for tension of a cable?
Yes.
I don't know.
It sounded like you were going to build a bridge or anything.
Nah, bridge, whatever. Just make it super strong, right? Well, then you're wasting material. Well, make it as cheap as possible. Well, then you're sacrificing tension, probably. So we want to figure out how much do we need to over-engineer this because our measurements are going to be off. Does that make sense? And then you're going to build in probably some extra because things happen. You're going to over-engineer it anyway. You're going to do the bare minimum, but we definitely want to at least meet our error. Clear? So let's try that. What I want you to do right now, can you please calculate the differential of t? Go for it. Do the differential of t, and I'll show you why we're doing that. How many independent variables do we have? Good. So you're needing 3 partials, dw, dl, dA. I'm going to work slowly up here. Let's check our work. I need you to work on your own for right now, but be checking your work as you're going. Did you get that far at least? Yes, no?
Yep.
Good for you. It's fantastic. Let's do that. Did you get the 8 and not like something crazy like 64, right? Okay, good. You still with me on this stuff? Are you finding it pretty easy to do differentials right now? Not too bad. They're just partials, you put them together. That's it. That's it. Now, that looks fantastic. What does that mean? What is that thing? Come on, at this point, after 2.5 hours, you gotta know what this means. What is that? What's this mean? Question?
On the bottom for the dA, is the whole bottom need to be squared or just the A?
Just the A, because that's the only thing you moved up there for the power -1.
Got it.
That's why we don't get a 64. Just move the variable. Okay, I was right on the little climax of the statement here. Come on, I was building up. I was doing a good oratorical style here. And we go, what's that actually mean? You should know. What's it mean? That's the approximation of the change in the value of the function. Change in height, yes, but the approximation of the change in tension based on this stuff when W or L or A or all of it changes, how it affects the height as an approximation. And now if you're okay with that one. Is it percentage error? No. Can you plug these things in? No, because these are actual changes, not percentage changes. This is percentage change. I'm going to show you how to do that right now. What we want to do, we want to approximate this right here is percentage error. It's the change divided by the value of the function. We can approximate it by that. And that's what we're about to do. So what we're going to do in general, so that we can plug in any numbers we want like forever, what we're going to do is we're going to take the differential that we just did and we're going to divide it by our function so that we don't have to plug in all these sorts of numbers. Because if you look at this, I don't have a W, I don't have an L, and I don't have an A. I cannot plug in anything for those values. I don't have a specific situation here, yet we can still use it to find maximum percentage error. Do you understand the concept? That's important. So we're going to do that. We're going to take our this divided by our this. That's what that means. Take your differential of t divided by the actual function. So that looks pretty crazy, but it looks like this. quick head nod if you're with me on that one. Now, we're going to divide, this is just the differential of t. We're going to divide the whole thing by what? That. Which means since that's one big term, I can divide it piece by piece by piece. Do you follow? So I'm going to divide the whole thing, which means this. This. And that. I'm kind of building this with you, but I want to make sure that we're clear on it. Are you clear on those pieces? Now, I'm also going to do one more thing. As I'm simplifying, because you guys see there's a lot to simplify, right? As I'm simplifying, I'm going to break this up into 3 absolute values and add them together. Don't subtract them, you're going to lose error. This negative needs to be associated with this thing, and then we're going to create 3 absolute values. Do you follow? Can you tell me what simplifies here? Pretty much everything except for what?
W.
So it's that in absolute value. Do you follow that? Plus, oh yeah, I see the 2. That's going to be on the numerator. And then I'm going to have a DL for sure. On the denominator, I'm going to have an L. 2 times DL over L. Now, why am I doing the DL over L? Let's think about that. Think about what this means, and think about what we're about to do with it. Plus, last one, it has to be negative because we're adding absolute value. We have to have the negative in here, so I know it's going to be negative. What is it going to be? What's on the, what happens? dA over A. A is on the denominator. A is on the denominator. I know it's just algebra, but just algebra can be kind of screwy here. Show of hands if you feel okay with that one. Now, let's think about what this actually means. What is dW over W? What is dL over L? What is dA over A? What is this thing? This is percentage maximum error. This is the amount that it changes over the total. That's a percentage here. This is always approximated by the differential of the function over the function. That is exactly what this and this and this are giving you. This right here is the maximum error, percentage-wise, of W. It is the change in W over W. That's what it is. It's just given to you as a percentage. This is the maximum percentage error of length. It is the amount that L changes divided by L. And this is that. So all we got to do is plug some numbers in. That's it. So we're going to have, what's the dW over W? Well, it's plus or minus 1%, right? And then we got 2 times plus or minus plus is a negative even relevant, honestly?
Professor, those are absolute value brackets, right?
Yeah. Are we talking about vectors? Or is that what you were trying to draw the conclusion, or no?
No, it wasn't.
Okay. Yeah, absolute value. Yep. Sorry, is that not?
No, it is, but I was just...
Yeah, we
I don't
are
know why we're
because
using the plus or minus if we're using the absolute value, so I'm just like going, it's automatically going to come out positive. Right?
they are. Yeah, absolutely. But I have them in here first so that I can kind of eliminate it, I suppose.
Okay.
So I'm not doing 2 things at once is what I'm doing. But yeah, the maximum error here is 0.01. Maximum error here could be 2 times either one of these. Absolute value, that's 0.04 plus, well, that's positive, another 0.02. How much altogether? 7%, 0.07. So engineering people, what we've determined in this scenario, if our measurements are this accurate, disregarding what our weight and length and A value actually are, we know that our cable tension is going to be off at most 7%. We could underestimate or overestimate at most 7% of the total value of the tension that we find. That is the idea. That is one way that we can use differentials to our advantage. Did this illustrate the concept well for you? Do you guys understand this? Are there any questions, at all? You sure? All right. Well, we are done with this section.